Hey, welcome back to Math with Patrick. Today is January 8th, and we are solving the 8th problem in this Daily Epsilon calendar. So let's get on into it. This one says that y is a positive integer, and x is equal to this sum right here, and x is also a power of a prime. So there's a lot of vocab going on, so let's define each part real quick. When it says that y is a positive integer, that means it could be 1 or 2 or 3 or 4 or so on. It can't be 0 because 0 is not positive, nor can it be negative. And an integer just means a whole number, so it can't be like a fraction or anything. So y is going to be an element of this set right here. And in another video, I actually defined this set to be the natural numbers. I like to think that the natural numbers start at 1 and count up by whole numbers. So this is what I'll write. Y is an element of the natural numbers, or in other words, it's a positive integer. And a power of a prime, this part means that I'll have some prime here, and prime numbers start at 2, 3, 5, 7, 11, 13, and there's an infinite number of them. And they are numbers that can't be broken down further by multiplication. Or in other words, if you found their factors, it's always going to be 1 and itself. As a quick aside, 1 is not prime because that 1 and itself, these just need to be distinct or different. So 1 is not a prime number. They start at 2 and they keep on going up. And a power of a prime, this means that I'm raising this prime number to some exponent, and this n right here could be 1. For example, 11 is a power of a prime because it's just 11 to the power of 1. It's a little trivial, but it still counts. Another example would be 49, because 49 is 7 squared. And so this power, or this exponent, could be any whole number. In fact, it's going to be another natural number here. So over on this side, we established that this x that we're trying to solve for is going to be some power of a prime number. And on the left side, I just wrote out the whole sum. And so this dot, dot, dot just kind of implies that I'm going to have a whole bunch of terms on the inside, and it's going to follow some kind of pattern. And the pattern is just that this exponent is going up 1 by 1 until we stop at y to the 7th. From here, I don't really know where to look except just trying some numbers out. Looks like y is some positive integer, and so I'm just going to pick the first one, being 1. So if y is equal to 1, and that is a positive integer, then I can say that x is equal to 1 plus 1, that's me plugging in the 1 here, plus 1 squared. 1 squared is still 1, and so when I add up all these terms, I'm just going to get a whole bunch of 1s added to each other. Adding up all of these 1s gets me an 8, because I have 8 1s. So x is going to be equal to 8 when y is 1. All right, and I need to show that this x is a power of a prime. I know that 8 is 2 times 2 times 2, or 2 cubed. I also know that 2 is prime because when you break it down into its factors, it's just 1 and 2. There's nothing else. So I found it. X is equal to 8, and that's the answer for today's problem. So that was weirdly easy. But I have another question. So I checked the first number for y and it worked. So couldn't I check another number for y and maybe I'll get another power of a prime? It just happened so quickly. Surely it could happen again, right? Or is the solution the only one? So that's what this epilogue is about. I think I could actually set out and prove that I could not get another power of a prime from this sum of y's, and it'll take a lot of pretty heavy math. So let's just try it out. So the first thing I'm going to do is investigate this large sum right here, and I would like to be able to write it with some factors or things being multiplied. That's just because eventually I'm comparing it to a power of a prime. And so I would like to be able to compare things being multiplied to things being multiplied, not added. So I'll take this sum, x, and it's adding up all those y's. And again, my goal is to rewrite this. So I'm going to do something a little strange. I am going to do x times y right here. I'll say x times y is equal to. And what this will do is tack on another y to all of these. And essentially, all of them are going to get, well, another y. So that 1 at the start is going to turn into a y. That y will be a y squared, and so on and so forth until this turns into a y to the 7th. And this last one, multiplied by y, is y to the 8th. If I take this bottom sum and subtract the top one, on the left side I get xy minus x. On the right, all of these terms besides just 2 are going to cancel out. This y to the 7 with the y to the 7 down here will cancel because I'll subtract this, so that minus that will be a 0. And this bottom sum is going to have all the appropriate terms to cancel out with this top one, all the way until y to the power of 1, or just y. So all those middle terms cancel, and I'm left with y to the power of 8 from here, minus, and then again, all these go away, minus just this 1. Well, that's cool. I feel like I simplified it a lot. I now don't have this long list, and rather I just have, well, something a little bit shorter. Ultimately, I did want to investigate the sum x, and so I will isolate it in this bottom equation. I can factor out an x from both of these terms on the left side, and then I can divide both sides by this y minus 1, y to the power of 8 minus 1, over y minus 1. Another concept that I'll bring to the table is some factoring. So I see right here a difference of squares. And difference of squares factor as such. If I have a square number here, subtracting away another square number, I can factor them like this. So the first number up here, if I think of something squared to get y to the power of 8, that's going to be y to the 4th squared. And then 1 squared is just going to be the same thing as 1 from here. So I know that I could factor the numerator by taking just that y to the 4th minus a 1, and then multiplying it by y to the 4th plus 1. This one's kind of interesting because I have yet another difference of squares here. I could write y to the 4th as y squared squared. So I can break up these factors even further and get y squared minus 1 times y squared plus 1. And then there's one more difference of squares. This one can be y plus 1 times y minus 1. And finally, I feel like I've factored it all. Let me collect it up. And finally, I noticed that the y minus 1 on top cancels with the factor of y minus 1 on the bottom. And so I'm left with x is equal to y plus 1 times y squared plus 1 times y to the 4th plus 1. And ultimately, this was my goal. I wanted to show that x could be something multiplied or several factors, just because it's going to be nice to try to compare it to the power of a prime. So I want to see if I can find a power of some prime that equals this, or maybe I can prove that this will never actually happen. Just as a little reassurance that this formula works, earlier I tried y equals 1. And so if I take a 1 and plug it in all those spots where I have y's, then I should get 8. Because 1 squared and 1 to the 4th, they're both just 1s. And then I have a 2 times 2 times 2, which is 8. Cool. So this formula checks out, at least for y equals 1. That gives me a little bit more confidence that this formula does actually represent the sum, just written in a different way. According to what I'm trying to find, all of these need to all be powers of the same prime. And that's because if one of these has, say, another prime included in it, then I can't express x as a power of just one prime, because then I'll have another one to deal with. So all three of these factors need to be powers of the same prime for me to be able to write x as a power of some prime. Let's take a look at this first one. So if y plus 1 is equal to p to the power of a, I guess I could isolate y. Y is equal to p to the power of a minus 1. And I'm going to try squaring it and comparing to what happens in here. Y squared looks like I have a product of binomials. So I'll do the product of the first, and then I have twice these two multiplied to each other, so minus 2 p to the a, and then I have this last term multiplied by itself. So negative 1 times negative 1 is a positive 1. And I said that I wanted to compare it to this y squared plus 1. And so I'll just add a 1 to both sides of this equation. Y squared plus 1 is equal to all of the same stuff, and then just plus a 2 at the end. And I'd like for that to be equal to p to the power of b, another power of a prime, and I am going to compare them here. So I don't know if these are equal. I'd like them to be equal because I'm saying that y squared plus 1 could be this, and y squared plus 1 could also be p to the power of b. On the left side here, I guess I could think about this a different way, where this is just a multiple of p. I guess I can show this because I could factor out just one p from both of these terms, and I get p to the 2a minus 1 over here, minus 2p to the a minus 1. And ultimately, when I take some prime and raise it to some power and do all this multiplication, this right here is just going to be a whole number. So I could factor out a p and get some whole number, which I'll represent with, I guess, z1, z for integers. And then I'll add a 2. And the same thing is going on over here. I know that p to the power of b, that's just p, or that prime, multiplied over and over and over again. And so that could be p times some integer, and I'll call that z2. Then let me get those p's on the same side. So I'll subtract this one and put it over there. 2 is equal to p times some integer minus p times another integer. And how about I'll factor out those integers? Now, when I do that factoring, z2 minus z1, these are both whole numbers. So when I do the subtraction, I'll just get another whole number. And so I'm going to call that z3, just to represent that I get some kind of whole number out of this. And that should be equal to 2. And I guess finally, maybe let me isolate this p, because that's what I'm kind of searching for anyways. P is equal to 2 divided by some integer. Now that's a little strange. I know that 2 divided by, well, most things would give me a fraction, not even a whole number. It looks like the only integer I could pick to make this fraction prime is 1. There's nothing else that will work. Or in other words, p has to be 2. There's no other prime that would satisfy these conditions besides 2. And we already found that. 2 cubed is 8. And so that shows that there are no other primes that I could raise to any power to get this sum. So the answer, pretty easy to find. It was just the first value of y that I checked, y equals 1. And it took a lot of heavy lifting to prove that no other primes could work. So, that's a problem. Quite a long epilogue today, but I wanted to show that the one solution we found is the only solution. So thanks for coming along for this ride. Today is January 8th. We are all done with this problem, and I'll see you tomorrow. Bye.